So a gray code is simply a special way of representing a, a word in such that only one bit changes between successive words. For instance, you have 001 representing 0, and then you have 1 as 001, and then 2 0011, 3 0010, and so forth. It shows that only one bit changes between successive words. A gray code incrementer, and the good thing about the gray code is that it limits the number of switching, which in turn makes it more efficient compared to ordinary binary code. A gray code incrementer simply finds the next gray code in this particular sequence. So today we're going to design a gray code incrementer. We're going to design it in an efficient way to make the circuit a bit more scalable. So this is a circuit. Since there is no specific way of incrementing from in binary in gray code from one word to the next, what we are going to do is we are going to change our gray code to binary, then increment it, and then change it to binary again. So for you to change from gray code to binary, this is the formula that you simply use. And for you to change from gray code to for you to change from binary to gray code, this is the formula that we'll be using. It's very simple to prove this. You can just look at the sequence, and will mostly tell you that the ith bit, for instance, bi will be equal to gray code of the ith bit XOR to the binary of ith bit plus 1. Okay, so now to designing it, what you're going to do is simply open your favorite for me, I'm using Visual Studio here as my editor, and then what you're going to do is you're going to make a folder in wherever you are. You're going to make a folder in wherever you're going to implement your design, and then just name it gray code. Okay, and then open it. Then we're going to have a file, a VHDL file. All right. Then we're going to start with importing our libraries. After that, you can have our entities. All right. So looking at our design, we have two inputs, which is a clock and reset, and then we have an output, which is going to be Q. All right. So we have two inputs. So we have a clock and reset, which are inputs. And then we have Q, which is going to be our output. And Q is a logic vector, because it will be from 4 bits, it should be 3 down to 0. Perfect. All right. So we basically have a couple of signals also. So we have this one as our current state of our D flip-flop. We have a D flip-flop, and then this one is our current state of our D flip-flop. This is our next state, and then we have B and A's signals in this circuit. So let me see. All right, so let's define our signals. So we said we have this is our current signal. So guys, should start with signal. This is our current and we're going to name these ones, and then we also have to next we have A, and then we have B. All right, and these ones are signals, and we're going to make them unsigned because we'll have to add +1 when we're incrementing. Okay, unsigned, and they will be 3 down to 1 down to 0. Perfect, we have our signals. Right, so this is our output. So basically we have our next state logic. Our next state logic begins from here up to here. This is our next state logic, and then we have this one as our register, and then this one as our output logic. All right, so back to our code. We say we will first of all start with our register logic, and then we will go to our next state logic. And then we will go to our output logic. Perfect. So in our register logic, we simply need to have a D flip-flop with a reset. Okay, then we're going to be a process clock as our sensitivity lists, and also we're gonna have our reset. All right, then we say perfect. So our reset is asynchronous, which means we first of all have to check if our reset is 1. If our reset is 1, what do we do? If our reset is 1, definitely this our current state is going to be 0, 0, which means we have resetted our register. So all right, else if. So now we said that our reset is not 1, then we have to check our clock. This is going to be a positive edge D flip-flop or register. So we're going to check if we have a raising edge. And we're going to check if we have a raising edge of the clock. What happens then? Right, so let's just first of all close our if. All right, so if we have a raising edge, then we pass along our next state to be our current state. So then we say that our current state will be next state. Perfect. And with that, we are done with our register logic. Now let's go to our next state logic. So what is basically happening in next state? In next state, now we have to find A, B, and then this, and then our next state our next state input. All right, so for this particular area here, so we have A, then we say, so this one is in a gray code, so we need to take a gray code and then binary, and then find in order to get our binary. Okay, so essentially what we say is we take G register, which is our current state, which is this signal here basically, and then we XOR with 0 concatenated with a from 3 down to 1. All right, so I know you may be wondering what's going on here. Okay, so basically in order for you to get in order for us to get our binary form of this gray code, we have to take the gray code and then XOR it with shifted bits with a 0 with replaced by a 0. So shifted bits to the right, bits shifted to the right and replaced by a 0. That's what this equation here is saying. Okay, this one will give you binary. So now A is in binary. So after A being in binary, so we have now to increment our logic in order to get B, which is now going to be incremented. So you take just A, add 1, gives us B. Now, so here we can say that we had gray to binary, and then here we said increment, and then we're going to say we've incremented it, so we say binary to gray, which is going to be, now we'll be calculating our next state register, which is this one now. All right, so we say that we have our next state is going to be B XOR zero, concatenate it with B three down to 1. All right, so here now this is now going to be in gray code, right? Then we'd have found this one, which is now in gray code. Right, so now we calculate, now we write our next state logic, which is simply, this is our current state to our output. So our output logic is that our output logic is that Q, which is our output, will be getting but remember, this will be getting our current state, which is G register here. But remember, this G register is unsigned, yet our output is std logic vector. So to change that, I simply say std logic vector. Perfect. Okay, so this seems good to me. Now let's test it. by opening, for me I'm using model sim, so open model sim. It's gonna take a bit, of time. And then now you create a new project. You have to browse to locate it, to create a new project inside where you opened your grayscale, which is right here. Okay, then you create a new project called gray code. And then you can say add existing, and then you'll be able to find the .vht file that we just created. Then we compile it. Says that we have an error. Let's see where the error is. It says could not find work.gray code. Could not find work.gray code. Number 12, line 12 gives you this is a problem. Let's try again. Still have an error. Number 21. Compile again. Oh, still have an error. Still number 21. Oh yes. All right. Compile again. 2 more errors. Oh, identified register. Perfect. So now it's working. Then now it's time to simulate. select all inputs, then click the small icon to make it look better, and then we select our clock and make sure it's clock. Our period is going to be 100 picoseconds. Just leave it like that, no need to change. Say OK, and then we now have to reset our register. Let's reset it by forcing a 1 with a delay of 0, which means it will start from 0 picoseconds. And then let's force it again to have a 0, but this time it's going to be delayed and we start from 100 picoseconds. So we are simply resetting our registers for one period of our clock cycle. Okay, after doing that, then we now run and see what happens. Oh, we ran for a very short time. Okay, so we're gonna have to reset again and then set our clock, and then we have to reset our register by forcing a 1 from the beginning, and then after that, sorry, not clock, after that we force a 0 but delayed for 100 picoseconds. Okay, then to see our entire, because our period is 100 picoseconds, so let's run it. If you run it for 1000, then you'll be able to get around 1000, around 10 grayscale words, gray code words, and we have a total of 16. So let's run it for around 1500, which will be able to be sufficient enough for us to observe something. So do that and then we run. Okay, so we are expecting that in our output we are simply expecting that we're going to have 000, 001, 00111, 0010, like that. We're going to have this sequence until you get to this the last one, which is 100, and then we'll drop around. So let's see if we are observing the same thing. So in the beginning, so let's just fit this. So this is our Q, which is our output. So we have 000, we have 001, then we have 0011, then we have 0011. Let's see from output, yeah, from 0001 we have 0011, which is true right here, and then the one following that is 0010, which is right here. So it seems like our incrementer is working just the way we expected it to increment. All right, so that's how you design a gray code incrementer, and this is the code to do it. So see you in our next design.